right? But this RMS value is a general term. It is not only related with Fourier series. For any function f of x, you can always find the root mean square value. So physically, this root mean square value is has some meaning in different context, depending on which the function f of x is represents. Whether f of x represents any movement of an object or f of x represents some other thing. So depending on that, the meaning of RMS will be decided, right? But how the RMS value is calculated? You know already, right? Any function will be defined only in the interval a comma b, right? Functions are defined in the interval a comma b generally, right? So RMS value of any function can be defined as, yeah, it is a number, so it is a square root of a number. What is that number? The number is integral a to b. That is where the function is defined. You have to integrate over that integral, and you have to put f of x square. Suppose if f of x is sine x, then f of x square is sine square x. Suppose if f of x is x plus sine x, then f of x the whole square is x plus sine x the whole square. Dx divided by the length of the interval. You have to divide it by the length of the interval. So this is the definition of RMS value. Now we should connect this RMS value with our Fourier series, and we try to find certain things. So for that connection only, we have to use the Parshall's identity. So Parshall's identity connects RMS value with our Fourier series. So that Parshall's identity is defined by the Parshall's theorem, but theorem statement only you need, proof no need, right? So what the theorem statement says: if the Fourier series of the function defined in the interval c comma c plus 2l. So we know in Fourier series the functions are defined only in the interval c comma c plus 2l, where the 2l is nothing but the periodic length. 2l is nothing but the periodic length, and this you know, this is the form of the Fourier series. After finding a0, an, and bn, we can write any periodic function in terms of sines and cosines, provided it satisfies the Dirichlet conditions. But how it connects with the RMS value? It connects the RMS value with the coefficients of the Fourier series. What are the coefficients? A0, an, and bn. So it's nothing related with cos theta sin theta, but whatever a0, an, bn you are finding for the Fourier series, that value, if you calculate like this, that is square root of a0 square by 4 plus 1 by 2 summation 1 to infinity an square plus bn square. This value is exactly equal to the RMS value. Otherwise, if you square both sides, right? So left hand side, this is RMS square, RMS value square. This is RMS value square. So if you square the RMS value, that is 1 by 2l c to c plus 2l f of x the whole square. So 1 minute. This is the last time so that I'm right. So this is the square of the RMS value, and this is the value already known from the Fourier series, because you already know a0, an, bn through the Fourier series. So this is the relation between the RMS value of a function with the Fourier coefficients a0, an, and bn, and that is stated by the Parshall's theorem. So Parshall's theorem states, if the Fourier series of the function exists, then the Fourier coefficients has this type of relation with the RMS value of the function. So it has lot of applications in lot of real world problems. In mathematics, as I told already, original Fourier series application is in the wave theory, right? So it is movement of waves. It may be electrical waves, or it may be water waves, or it may be thermo waves, or it may be magnetic waves, whatever it may be, but it deals with the wave theory. So it has lot of applications are there, but at the same time, it has some simple applications in mathematics itself by evaluating certain infinite series. So here also we can use this relation to evaluate certain infinite series, right? But that is not a real application. Don't think only for infinite series evaluation only we are using Fourier series. Not like that. But in mathematics, there are infinite series which are difficult to evaluate. But using Fourier series, we can evaluate with the help of RMS value. With the help of RMS value. In some book, they use the notation y bar for the RMS value, and they use here y bar square. Even in Veerarajan, you can find this notation. Y bar represents the RMS value of the function y equals to f of x. right? Okay, now we'll see one problem where we are using the partials theorem, where we are using the partials theorem. So here there's a problem is there, find the Fourier series of the function, find the Fourier series of the function f of x equals to x square defined in the interval minus pi to plus pi. So this is c is minus pi, c plus 2l is plus pi. So what is totally length? The total length is from minus pi to plus pi, from minus pi to plus pi. The total length is 2 pi distance. For that we have to find the Fourier series first, right? For that we have to find the Fourier series, right? So for that we go back to whatever we have discussed in the last class. So in the last class when we discussed the problem, Fourier series problem, right? One of the problem is in 2.9, it is in the 2.29. So first we see that problem. So this is the problem. Here they are asking find the Fourier series of the function f of x equal to x square, right? So this type of problem we discussed in the last class itself. So what we found there, we just found, right, a naught by using the formula an and as well as bn, and we found finally the Fourier series representation of the given function. I will see the I will tell you the Fourier series representation, right? So this is a naught. So this is the Fourier series representation. Find the Fourier series of the function. You have to find a naught, an and bn, right? So now what we are going to do is not again to find the Fourier series, not again to find the Fourier series. Just we take the representation. Just we take the representation and then we have to apply the Fourier that is partial theorems in this problem, right? Okay. Before that, I want to tell one more thing also in now itself so that it will be easy to understand. Right, because last class itself I explained the off-range cosine series and off-range sine series also, right? So better you relate that also with partial theorem now itself. So just now I told this is the representation or this is the relation between the Fourier series and the partials, that is RMS value. Left hand side is RMS value square and right hand side is partials, that is Fourier coefficients. Right. But last class we discussed off-range cosine series. What is off-range cosine series? There the function is a even function defined in the interval, 0 comma 1, defined in the interval 0 comma L, defined in the interval 0 comma L, that is defined only in the half of the interval, defined only in the half of the interval. And then in Fourier cosine series you have to find only a naught and an. There is no need to find bn because bn is 0 in half range cosine series. Similarly, I explain what is half range sine series. In half range sine series, you have to find only bn. There, a naught and an become 0. A naught and an become 0. Right? So, with these two things, we can define the relation between, right, half range Fourier series coefficients, that is a naught an, with the partials, with the RMS value. Their RMS value is defined in such a manner that since the interval is defined only in the half of the interval, not for the full interval c to c plus 2l. So here we have to put 1 by l, not 1 by 2l. The formula is 1 by l, 0 to l, f of x the whole square, and this is a naught and an value. So here there is no bn. See, this is the relation between RMS value and a naught, an, bn for the general Fourier series. But here this is a relation between RMS value with the off-range Fourier cosine series. Similarly, this is the relation 1 by L 0 to L f of x square dx is equals to bn square. So this is a relation between the RMS value with the off-range Fourier sine series, off-range Fourier sine series, right? So you just mark up this relation, right? But how to use it in the formula, how to use it in the problem, that is very, very important, right? For that, I'll give you one simple example. So when you take this Fourier series problem, find the Fourier series of the function f of x equals to x square from minus pi to pi, and we found that f of x square is a even function in the interval minus pi to pi. So we can able to find only a naught and an, and this is the Fourier cosine series, half-range Fourier cosine series of the function f of x to x square, right? Half-range Fourier cosine series of the function, right? Because their bn's are 0. Their bn's are 0. Okay. But originally the function is defined in the interval minus pi to plus pi. Originally the function defined in the interval minus pi to plus pi. But because of the even nature of the function. Remember here they were not asking find the Fourier cosine series. They were asking find the Fourier series. But by understanding the function as a even in nature, we found only a naught and and we automatically taken bn as zeros, right? So there is a difference between in the problem itself they are asking find the half range cosine series, or you are in the problem they are asking find the general Fourier series, but in when you are doing the problem you can understand that the function is a even function. So here the problem is find the Fourier series. They are not asking simply the function is defined throughout the interval 2 pi, right? But since you understand the function is a even function, so that you found only a naught and then bn, an and bn automatically become 0. But when we use the Fourier series identity, we have to use only this identity, not this. Because in the problem, they are asking find the general Fourier series. In that general Fourier series, fortunately, you are getting a bn equals to 0, right? Because of the even nature of the function. But they are not asking Fourier cosine series, right? They are asking only general Fourier series. So that you have to use only this formula, right? Only this formula. So 1 by 2l is 1 by 2 pi, c to c plus 2l is minus pi to plus pi, f of x is x square, a naught value, a n value, but fortunately bn value is 0 for that particular problem, right? That only here, right? Because people confuse with Fourier cosine because they are thinking x square is a even function, so directly they write Fourier cosine series, not like that. So that yesterday, last class I told, even for x square you can get an odd extension. If for a even function you get a odd extension, right? So in the problem they're asking find the Fourier series. So that is a general Fourier series. So for that a naught value is this, a n value is this, bn value is 0. So you can take that formula. So here they are taking bn also, but that is fortunately 0. On the left hand side 1 by 2l is 1 by 2 pi minus pi to pi, f of x is x square, so that is given here, and then whole square dx, right? And they calculate, when they calculate, a naught square is 2 pi square by 3. So if you square this term, this become 4 by 9 pi power 4, right? 4 by 9 pi power 4. But automatically one 4 in the denominator. So that 4, if it cancel, then it becomes 9 pi square. It becomes, so that is this 4, right? Then it becomes 9 pi square, right? See, this is pi power 4. So what you get? Pi power 4 is there, 9 is there. This 4 in the numerator and this denominator 4 will cancel out each other, right? So that they are putting, and then for an square, 4n square minus 1 the whole power n. So remember, an is 4 by n square minus 1 the whole power n. So an square means squaring the right hand term. So it becomes 4 square is 16, n square square is n power 4, and then what is minus 1 the whole power? N square means, right? Whatever number you are getting. So what number you will getting? Either you get 1 or minus 1. When n is odd, this is minus 1. Whenever n is even, this become plus 1. So you get only two numbers, minus 1, comma, plus 1. But if you square that numbers, automatically it will be plus 1 always. It will be plus 1 always. So what you have? You have pi power 4 by 9 plus, so this is pi power 4 by 9 plus half times whatever the value over here, 16 by n power 4. So 16 by 2 cancel, it is 8 by n power 4. It is 8 by n power 4. So now what you have to do now? You have to write this term on one side. right? You have to write these terms on one side, and then you have to evaluate them on the other side. You have to evaluate this term on the other side, right? So whatever I told now, it is there here. This 4 will cancel. 16 by n power 4 will cancel. So this is in the left hand side. But in the right hand side, it is 1 by 2 pi minus pi 2 pi x square the whole square, right? But x square the whole square is x power 4. X square the whole square is x power 4. And one more thing, x power 4 is a even function. So minus pi to plus pi can be written as 2 times 0 to pi x power 4. Right? That time this 2 will cancel. If you integrate x power 4, it becomes x power 5 by 5. And if you put the upper limit, it is pi power 5. Lower limit 0. So 5 power 5 by 5 pi. So 1 pi cancel. So it is pi power 4 by 5. So that is the right hand side value. And in the left hand side value is, right, 1 by 4, right, uh, that pi square by 4 plus 1 by 2, right? So here you just try to understand. This is 1 by n power 4, right? Not n square, because when you square this term, 16 by n power 4. So 16 by 2, 8, right? So this 4 cancel. So pi power 4 by 5 is in the right hand side. This pi power 4 by 9 goes this side. So this becomes minus pi power 4 by 9. And if you take the LCM, 9 minus 5, 4. 9 5s are 45. So this side 8, this side 4 by 45. So 8 and 4 cancel out, becomes 2. And this 2 comes in the denominator. It becomes 44 into 2, 90. So what do you get finally? Summation 1 by n power 4 value is pi power 4, 90. Pi power 4, 90. Right? So this is the value for the term summation 1 by n power 4. Summation 1 by n power 4, because that the only they are asking in the, right? So don't think the summation 1 by n power 4 is pi power 4 90 is an application of Fourier series, but this one of the application of Fourier series evaluating certain infinite series with the help of partial identity. But in examination point of view, this type of problems are very, very important. See, even in analysis, they asked each and every year, 2005, 7, 8, 9, 10, 11, 40. So each and every year, regularly this type of questions will be asked, particularly Fourier series problems with partial identity, right? So that I explain this problem. So in the same manner, you can apply the Fourier series for general Fourier series, as well as for off-range series, for off-range cosine series, as well as off-range sine series, right? So up to find Fourier series, you have to find the Fourier series representation as it is, just we seen in the last class. Only when we evaluate the infinite Fourier series, that time only we have to use Parshall's theorem. So we may ask, sir, how we understand we have to use Parshall's theorem during this time? Means, right? When you see the original partials or original Fourier series, you have infinite terms like 1 by 1 square, 1 by 2 square, 1 by 3 square, 1 by 4 square. So this is nothing but a n term, right? A n term. So that is 1 by 1 square, 2 square, 3 square, 4 square. Otherwise, you can see here, a n term is 4 by n square. B n term, no. A naught is a constant. So the only infinite series here it is in the form of 1 by n square. But in the problem, they are asking 1 by n power 4. So 1 by n power 4 is not at all in the Fourier series itself. That infinite series term, it is not at all in the Fourier series itself. So even if you put some value for x or something, that won't gives you 1 by 1 power 4 plus 1, 2 by power 4, 3 by 4, it won't get. So for that case only you have to understand, you have to use Parshall's theorem, because in Parshall's theorem you can square the Fourier coefficient. So if you square that number n power square, then automatically it will come n power 4. So if it becomes n power 4, so that only printing mistake they done here. So this is not square, this is n power 4. So automatically when you square the an term, so 4 by n square, it becomes 16 by n power 4. So now we have n power 4 term. So this is an idea that we have to apply partial theorem, because in the original Fourier series representation there is no format for 1 by n power 4. So that, but it is there only 1 by n square. So if you square the term, you will get 1 by n power 4. For that, instead of you putting straight away some value for x, you are using the partials identity. You are using the partials identity. I hope, right, this will help you to understand how to use partials identity. It's only a formula. You have to mug up this formula and you have to evaluate this integral separately, and you have to put the Fourier coefficients in the infinite series, and then you have to keep the infinite series on one side and take all the terms on the other side. Then automatically you will get the value for the infinite series in the last line. So with that, right, so I hope this section is understandable, right? So now I can move on to the next section of Fourier series, that is the complex form of Fourier series, right? So here there's no problem is there. So here it is only a small derivation. How to write Fourier series in terms of complex form, that is in terms of complex valued function. You already know what is a complex number. A complex number is nothing but it is of the form a plus ib, right? Any number which has a real part and it has a imaginary part, and with the imaginary number I, with an imaginary number I, right? What is this imaginary number, right? How, why it comes, right? So you know, whenever you solve this type of equation, x square minus 1 equals to 0, then x square is equals to 1, then x is equals to plus or minus 1. So you can find the solution for this equation is either plus 1 or minus 1, right? So in this case no problem. But if you take the equation x square plus 1 is equals to 0 and x square is equals to minus 1, then x is equals to then x is equals to square root of minus 1 plus or minus, right? So this square root of minus 1 we can't understand, because squaring a number is always plus, but here squaring a number you will get minus 1. So this is an imaginary one that is denoted by I, that is denoted by I. So what is I? I is nothing but an imaginary number which is equivalent to square root of minus 1. Using that, you there are a lot of uh, 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 things are there, right? You can write a complex plane where this is the real part, this is the imaginary part, and you take any complex number a comma b in the complex plane, because you already study complex plane in your school itself. A comma b is a point and it is denoted by a plus ib, where a is the real part of the complex number and b is the imaginary part of the complex number. But here we are try to write in terms of complex valued function. What is complex valued function? Suppose you write f of x equals to e power x, then it is a real number. It is a real valued function because x is a real number. E power x is also a real number, e power 1, e power 2. But if you take a function f of x is equals to e power ix or e power minus ix, then this became a complex valued function because I is the complex number. And you know the presentation of this e power ix can be written as cos x plus I sin x. Cos x plus I sin x. Right? So similarly, e power minus ix can be written as cos x minus I sin x. So e power ix is a complex valued function because it has a complex number I. So here also we are going to write this Fourier series which has a trigonometric function cos x and sin x, and we try to write in terms of complex numbers, complex valued functions using this relation. So we have to write cos theta and sin theta in terms of e power theta, in terms of e power I theta, right? So that derivation, writing Fourier series in another form containing the complex valued functions, then it is called a complex form of Fourier series. So the derivation is very simple. Within 5 minutes, I will explain it, but you have to follow it in a very careful manner, right? So you already know the Fourier series representation of the function f of x, and you already know what is a n representation and what is b n representation, right? So now only one thing what you have to know, you have to use this Euler's formula. It says e power I theta is cos theta plus I sin theta. This is already you know in school itself. Similarly, e power minus I theta can be written as cos theta minus I sin theta. E power plus I theta can be written as, or e power ix can be written as cos x plus I sin x. Similarly, e power minus ix can be written as cos x minus I sin x, right? And these two are complex conjugate. How? Because whenever you write a plus ib, then a minus ib is the complex conjugate of the function, complex conjugate of the function, or complex conjugate of the number, complex number, right? So these two are complex conjugate to each other. Now for these two equations, suppose you take this as equation 1 and this you take it as equation number 2, right? Then if you add these two equations, e power I theta plus e power minus I theta, right? Then I sin theta and minus sin theta will cancel because we are adding. Then here cos theta plus cos theta become 2 cos theta, and 2 comes in the other side. So cos theta can be written as e power I theta plus e power minus I theta divided by 2, right? That is one thing. Instead of plus, if you minus, right? You subtract both the things, e power I theta minus e power minus I theta, right? Then cos theta cos theta will cancel out. Then this minus this becomes minus of minus become plus. So 2y sin theta will come. 2y sin theta will come in the opposite side, right? In that case, you keep sin theta on one side, take 2y on this other side, 2y on the denominator. Then e power I theta minus e power I theta divided by 2y is the representation for sin theta. So now you can know cos theta is this, sin theta is this. But in the Fourier series representation, what is your cos theta representation? Cos n pi by Lx. N pi by Lx. So now in place of theta, we have n pi by Lx. So e power I in place of theta, n power pi by Lx, and e power minus I theta. So there also you have to put n pi by Lx, n pi by Lx, right? So we can write cos n pi by Lx as, that is cos theta as e power I theta plus e power minus I theta divided by 2. Similarly, we can write sin n pi by Lx as, right? So what sin pi by x? E power I theta minus e power minus I theta divided by 2i, divided by 2a. Once we write like this, we have to substitute this over here, over here. No need to substitute for a not anything. Only for in place of cos, you can substitute e power I n pi by Lx plus e power minus I n pi by Lx divided by 2. Similarly, in place of sine, we have to substitute e power I n pi by Lx minus e power minus I n pi by Lx divided by 2i. So what is the only difference? Here plus, here minus. Here there is no I, here I is there. But now, after writing cos theta and sin theta in terms of e power I theta, we have to group e power I theta terms separately and e power minus I theta terms separately. So when you group e power I theta terms separately, you have a n by 2. So that is here written here. And then plus bn by 2y. That is written here. Similarly, if you take e power minus I nx common, e power minus I nx common, right? Here I is missing, here I is there, right? Then automatically here the coefficient is a n by 2. Here also coefficient is a n by 2. But here the coefficient is minus bn by 2y. This is plus, but here inside minus is there. Minus bn by 2y. Minus bn by 2i, right? So an by 2, here bn by 2i for e power I, and for e power minus I, again an by 2 and minus bn by 2i. That is written here, right? Now we have to use one simple idea because I is present in the denominator. So once if I is present in the denominator, 1 by I is present in the denominator, we can multiply I and divided I, both numerator and denominator. So now the numerator is only I, but the denominator becomes I square. I into I square. So previously it is only bn by 2I, so only 1 by I, right? But now you are multiplying I and I, both numerator and denominator, because you have to find what is 1 by I, right? So in the numerator it is only I, denominator it is I square. But what is I? You already know I is square root of minus 1. So if you square this term, I square, what do you get? You will get minus 1, right? So numerator is I, numerator is minus 1. Otherwise it is minus I, right? Otherwise it is denominator minus I. So what happened? 1 by I become minus I. 1 by I becomes minus I. So here, when you take this 2I in the denominator to the numerator, this 1 by I becomes minus I, so that here, even it is plus here, I can write it as minus an minus ibn by 2. Similarly, the same thing happened in the reverse order here. Here, I is the denominator. If this I is the denominator comes numerator, one minus sign will come. That minus sign and this minus sign cancel out. So here an plus ibn by 2. So now I comes to the numerator. I comes to the numerator. So now what we have? We have a naught by 2. We have an minus ibn by 2 and an plus ibn by 2. So we have these three notations with the coefficients e power I and e power minus I. So now you have to give again a representation for C naught, Cn and C suffix minus n in such a manner that an minus ibn by 2 can be written as Cn, right? You may ask, sir, why it is Cn? It's just a representation, right? A naught by 2 assumed as C naught, and suppose when C is this is an infinite series, n varies on to infinity. So a1 minus I b1 by 2 can be written as C1. a2 minus I b2 by 2 can be written as C2. Similarly here a1 plus I b1 by 2 can be written as C suffix minus 1. a2 plus I b2 can be written as C suffix minus 2. But that is only a representation. Sir, how plus minus plus n become minus n? There is no plus and minus n. I am just representing a1 plus ib1 by 2 as C suffix minus 1. C suffix minus 1. But now I will tell why I am doing like that. So by this assumption, right, we can write a naught by 2 as C naught. Similarly, by this assumption, we can write an minus ibn by 2 as Cn. Similarly, an plus ibn by 2 as C suffix minus n. C suffix minus n. So now you forget all the other things. You just look at the infinite series. It has three things. One is midpoint 0, right? Another one is minus exponential. This one is plus exponential. So what you have to do now? Very simple. Even here n is varies from 1 to infinity, 1 to infinity, you will get only terms like C suffix minus infinity and C big number dot C suffix minus 3, C suffix minus 2 and C suffix minus 1. And C naught, then only it is C1, C2, C3 will go. Right? So now look at this. Look at this interval. Right? So here there are three things are there. One series, right? Even though it is put it as n varies from 1 to infinity, I just explain it, then only you can understand. Even though one series as 1 to infinity, another series also having value to 1 to infinity, but when you put n varies to 1, 2, 3 here, you will get only terms like C suffix minus 1, e power minus I, n equals to 1, so pi x by L, pi x by L. Similarly, when you put n equals to 2 in this series, you will get plus C suffix minus 2. right? So even though it is 1 to infinity, it is also from 1 to infinity. But here the values are C0, C1, C2, C3. It will go like that. But here the values are C minus infinity up to C minus 1, right? So this is the representation, infinite series representation of Cn from minus infinity to minus 1. And this is a number at 0. And this is the number where it moves from C1 to C infinite. Moves from C1 to C infinite, right? So there are three different terms are there, but the limit value are moves from minus infinity to minus 1, then 0, and then 1 to infinity. So totally, the total interval is from minus infinity to plus infinity. Minus infinity to plus infinity. Now I will tell you how to write everything in a proper manner. C A naught by 2 can be written as C naught. Okay, good. This can be written like this. Good. This also can be written like this. But now look at this. All these things are related in a single term. N varies from minus infinity to plus infinity. Cn e power I n pi by l. How? Because whenever n is negative, because here n varies from minus infinity to plus infinity. So whenever n takes negative value, this is equivalent to this one, right? So we may say here this Cn positive, here C suffix minus and negative. How these two things are equal? Remember, here minus sign are in the notation, but here the minus sign are in the series itself. So you see that it starts from minus infinity. So here I take the series from minus infinity to minus 1. In that case, this representation is equivalent to this, right? And when c equals to 0, sorry, when n equals to 0, right? E power 0, here n equals to 0, so c naught e power 0 is 1, so that time it value is equals to this. Similarly, when n equals to 1 to infinity, when n varies from 1 to infinity, right? N varies from 1 to infinity, right? Cn value also moves from 1 to infinity. In that case, it has a representation, same representation whatever it have seen. So this one infinite series consists all these three terms. When n moves from minus 52 to minus 1, this is equivalent to this. When n equals to 0, this equals to this. When n varies from 1 to infinity, this equals to this, right? So that they write in a single statement, n varies from minus 52 to plus infinity. N varies from minus 52 to plus infinity. Cn e power I n pi by l x. And this is called the complex form of the Fourier series because it has only one Fourier coefficient, that is Cn. And it is also doesn't have any cos or sine. It have a complex valued function e power I n pi by l x. So this is called as complex form of Fourier series. Complex form of Fourier series. But you may ask, sir, in the Fourier series, you have to find the Fourier coefficient. So what is the Fourier coefficient here? Here the only one Fourier coefficient, that is Cn, right? That is Cn, right? But how to find that Cn? How to find that Cn? That only you have to find here. So this is originally it is Cn, right? Not f of x. This is Cn. What is Cn, right? Just now we have seen Cn is nothing but an minus ibn by 2. Right? We know an formula. An formula is this: f of x cos n pi by lx dx. We know bn formula. Bn formula is f of x sin n pi by xl lx dx. So we know already an formula, bn formula from general Fourier series. So what is the only thing extra thing? Minus I. So here minus I, right? 2 is there. So we put 2 and 2 here, right? So what is this representation? This representation is nothing but an minus I bn by 2. So we have to substitute an separately, bn separately, and then divided by 2, right? So now there's no need to integrate. There's no need to integrate anything. So this is the representation for an, this is the representation for bn, right? But what you just take the common things. What are the common things? F of x is common, interval is also common, 1 by 2l, everything is common. What are the only difference? In an cos n pi by lx is there, in bn sin n pi by lx is there, and I is there, right? So now f of x is out, this is there. So now how to write this? Just now you have seen cos theta minus I sin theta, right? Cos x minus I sin x. That is cos theta minus I sin theta. 1 minute. Ah. Just now you have seen, right? Cos theta minus I sin theta is e power I theta. Now also we have the same thing. What you have seen here? Cos n pi by lx minus I sin pi by lx. It is also something like cos theta minus I sin theta. So cos theta minus I sin theta can be written as e power minus I theta, e power minus I, because e power minus I x is cos x minus I sin x. So this is the thing. So Cn is this. So if you want to calculate Cn, you can calculate Cn using this formula 1 by 2L C to C plus 2L f of x e power minus I n pi by Lx dx. After calculating Cn, you can substitute the Cn value here. That is the value for the complex form of the Fourier series. That is the value for the complex form of the Fourier series, right? Okay. So if you want to find some problem for complex form of Fourier series, very simple, right? I just explain one simple problem within a minute, and then we'll see one introduction to that next unit also, right? So 5 minutes introduction, so that next class I can straight away start the problem. Because of the time constraint, you are writing only cat 2 now, but you have to write your model exam by November 15th, right? Immediately after the Diwali holidays, and then after thing you have to write your university examination. So with this time constraint, so better we use the time whatever we have, right? So here I just explain how to find the Fourier series, complex form of Fourier series. This infinite series expansion you can already know. So just substituting the values for x, you can able to get this thing, right? So here they are asking find the complex form of the Fourier series of the function e power ax. But e power ax is not a complex valued function because there is no I is there. There is no I is there. But still we can find the complex form of the Fourier series for this function, right? So don't think, sir, you are finding complex form of Fourier series, the function is not complex form. That no need. E power minus IAX is a complex valued function. So whenever you multiply a function with complex valued function, the entire thing become a complex valued function, right? So here, as per the formula, what is f of x? Right? F of x is summation varies from minus infinity to plus infinity Cn e power minus I n pi by Lx. And what is Cn? Cn is 2 by 1 by 2L C to C plus 2L f of x e power minus I n pi by Lx. So you have to use only this formula in the problem, right? So you take the problem. So this is the notation. This is the formula. And where the function is defined in the interval minus pi to plus pi. So we put total interval is 1 by 2 pi minus pi to plus pi, and function value is e power ax, and multiply with e power I n pi by Lx. So I n pi by Lx, right? But here L is equals to pi, so pi cancel out. Pi cancel out. So it is simply e power inx. E power minus I forget. E power minus inx. So that it is here simply e power minus inx because pi and pi cancel out. So now we have to integrate this. Integration part is very simple because here both the functions are exponential functions. Both the functions are exponential functions, right? Since both the functions are exponential function, powers are added because you know e power a into e power b can be written as e power a plus b. E power a plus b. Powers are added. So here also you can add the powers. So e power a minus in of x, and then you can integrate e power ax. E power ax is e power ax by a, and then you can substitute minus plus limits. So when you substitute the upper limit plus pi, you will get e power a minus in pi, and then e power minus in pi. Similarly, you can substitute the lower limit also. You can substitute the lower limit also, and then you can find the total value. You can find the total value, right? So you may ask, sir, e power pi is there, e power minus pi is not there. Why? Right? Because when we write e power some constant times pi, right? So what is e power a pi? E power a pi is cos pi plus I sin pi, right? Cos pi value is minus 1, right? And sin pi value is this. So all these things are there, right? So you have to keep that in your mind, and according that you have to substitute the values. So this I don't want to teach because, right, this is only a substitution, and then uh, uh, so I just tell you how to write the Fourier series, complex form of Fourier. So after do some calculation, you will get Cn here, right? So once you get the Cn here, you have to substitute that Cn in the complex form of Fourier series. F of x is summation minus infinity to plus infinity into e power inx. What is this e power inx? This e power inx is nothing but this. Because in the complex form of Fourier series, after finding Cn, you have to multiply that with e power I n pi by Lx. That is the original complex form of Fourier series. Since L equals to pi, so L is equal to pi, so you have to multiply it, whatever Cn you found, with e power I nx. E power I nx. So that only they are written here. After finding the Cn value here, they are just multiplied with e power I nx. E power I nx. Right? Okay. So next some 5 minutes, I will just explain the definition of Fourier transform, because for second unit, I hope this is sufficient. General Fourier series, half-range Fourier series, and then whatever discussed with today, that partial theorem, and then complex form of Fourier series is more than sufficient for the Fourier series unit, because in all the problems you are finding only A naught, ANs, and BNs, right? So for next 5 minutes, right, I'll explain the definition of Fourier transform, what is Fourier transform, and the definition of Fourier transform, and next class we will see the problem. So stay with me for 5 more minutes. Very simple, because it is related with Fourier series, right? Same that off-range Fourier series, sine series process, the same idea will come, right? So what is Fourier transform? So the Fourier transform, the word itself tells it transforms certain things. So just like in Fourier series we transform the function f of x in terms of trigonometric functions like cos or sine, cos or sine, right? We transform f of x as in terms of cos x comma sin x. Where in Fourier series we are trying to write f of x in terms of cos x and sin x. Here also we try to write Fourier series. Here also we try to write the given function in terms of another format, right? That format is called as Fourier transformed format. What is the need of Fourier transform? Just like in Fourier series, if we transform a function, particularly a periodic function, in terms of sines and cosine, then it is easy to analyze the particular function. Similarly, here also f of x is a given function. If you transform that function using some idea as a Fourier transform, the Fourier transform is defined by f of s, right? So if you transform a function from f of x to f of s, then we can easily analyze the function in the form of f of s, right? And then after analyzing that, we can apply inverse Fourier transform, and we once again transform the format of the function from f of s to f of x. So here, there's no need that the function should be a periodic function. It should satisfy certain conditions. If such satisfies certain conditions, that function can be written in terms of Fourier transform. But for that Fourier transform, the fundamental theorem is there, that is called Fourier integral theorem, right? So this theorem is already shared, right? in the notes also, right? Just mark up this theorem. Based on that theorem only, we are defining the Fourier transform definition. Fourier transform definition, right? So, Fourier integral theorem proof is not need, but how to evaluate the Fourier transform, that is very, very important, right? So, I'll directly will go to the Fourier transform formulas. Then I will explain you, right, how to find the Fourier transforms, right? So, I directly go to the Fourier transform formula, right? So, whenever a function f of x is given, right, it has to satisfy certain properties, like it should be piecewise continuous and it should be absolutely integrable. All these things are there, but that is not at your level, that no need, right? What is the meaning of piecewise continuous? You know, the function should be a continuous function everywhere except at finite number of points. Apart from that, if it is continuous in all other place except at finite number of points, then it is a piecewise continuous function, right? Then it also satisfies certain conditions, right? But the conditions no need when we solve the problems, right? So that I'm tell you, you just mark up the Fourier integral theorem for 2 mark purpose. But when you do the problem, you have to remember only this formula. What formula? Whenever the function is given, right, you have to integrate the function from minus infinity to plus infinity, and you have to multiply it with e power ist. There in Fourier series, you are multiplied with cos and sine, but here you have to multiply it with e power ist. So it is something like the complex form of the Fourier series, because here in f of t, right, it may be for real valued function or a complex valued function, right? And here 1 by root 2 pi. 1 by root 2 pi is a constant. It is not length of the period of the function. It is a constant, right? So 1 by root 2 pi is a constant, and then f of t is the given function. So whenever if they ask find the Fourier transform, you just take the function, integrate the function from minus infinity to plus infinity, multiply it with e power ist, and then you will get a number. You will get a pure number, right? And since s is present is there, apart from s, all the other things should be a number only, right? All other things should be a number only. So finally you will get numbers multiplied with some function of s, some function of s, so that here they are denoted as f of s, because whenever you integrate the function with respect to t and you're putting the limits for t, all other things become numbers except this. In e power ist, in e power ist, I is there, right? E power ist, here I is there, here s is there, right? So finally it became a function of s, function of s, right? As I told already, there is a inverse formula is also there. There is a inverse formula is also there, that is called inverse Fourier transform. That is inverse Fourier transform, right? So that is there here in a nice formula. You can see both the things here, right? So 1 by root 2 pi f of x multiplied with e power minus isx 1 by root 2 pi. This representation transforms the function f of x into f of s. F of x into f of s. And this is called inverse Fourier transform. This is called inverse Fourier transform. This is called inverse Fourier transform. What does inverse Fourier transform do? After analyzing the function in f of s, if you want to get back the function or again in terms of f of x, right, you just use this formula. Which formula? You have to, after finding f of s, if you want to originally get back to f of x, you put f of s here, multiplied with e power minus isx, here plus isx, here minus isx, 1 by root 2 pi, 1 by root 2 pi same, but here you have to integrate with x, here you have to integrate with ds, here you have to integrate with ds. But both the formulas are comes from the Fourier integral theorem. That is, in Fourier integral theorem you can have two integrals in the Fourier integral theorem. From that integral only these two integrals comes, right? One integral is Fourier transform definition, another integral is Fourier inverse Fourier transform definition. But only one problem in Fourier transform is different authors use different notations, right? Even in Virarajan, what are you using for the offline classes, right? There you can see here they put nothing, they put only one, nothing, they put only one. No, simply they start with infinity. And here they put 1 by 2 pi. 1 by 2 pi. They put 1 by 2 pi in the inverse Fourier transform formula, and they put no constant in the Fourier transform. Why? Because this is one. This is comes from a derivation. In the derivation, some authors taken 1 by 2 pi as 1 by 2 pi as 1 by 2 pi as 1 by root 2 pi into 1 by root 2 pi. Because what is root 2? What is 2? 2 root 2 can be written as root 2 into root 2. In the same way, 1 by 2 pi as they take it as, wait a minute, I will write here. They take 1 by 2 pi as 1 by root 2 pi and then 1 by root 2 pi. Right? So they put 1 by root 2 pi, 1 by root 2 pi for Fourier transform operation, another 1 by root 2 pi for inverse Fourier transform operation. But for some authors, they retain 1 by 2 pi for the definition of inverse Fourier transform, and they put nothing here. But both are mathematically correct because you don't know the original derivation. In the derivation, some people taken this and some this, but both the formulas are correct. The same way, in some books, right? Some book, when they take the exponential, they put minus sign here in the formula and they put plus sign here. Same in another book itself, you can see e power minus isx in the Fourier transform and e power plus isx in the inverse Fourier transform. But both are correct. Whether you put minus sign or plus sign, both are correct because when you transform the function from f of x to f of s, and again if you transform from f of s to f of x, then automatically it will adjust. But you may ask, sir, if you transform only one form from f of x to f of s, suppose if you use minus sign, you will get different f of s. If you use plus sign, you will get a different f of s. Yes, you will get plus sign, you will get different f of s, minus sign, you will get another different. But when you apply inverse Fourier transform, again, then automatically, according that, it will change. If you put minus sign here, then you have to put plus sign here. Suppose when you transform it, there if you put plus sign in the beginning, then you can put, when you apply the inverse Fourier transform, you can put minus sign in the inverse formula. So mathematically both are correct, right? So this is the definition of Fourier transform. In this Fourier transform also we have Fourier cosine transform and Fourier sine transform formulas are there. Fourier cosine transform and Fourier sine transform formulas are there. And here there are only 2 or 3 standard problems are there, and there are certain properties are there, right? So next class we will see 1 or 2 problems in the Fourier transform as well as 1 or 2 properties, right? So if possible, right, I try to take some classes. Next week is not possible because it is Diwali holidays. I don't want to disturb you to Diwali. But after Diwali, before the pre-university examination, right, I will take, right, because everybody needs classes. Okay, that is the problem, right? In offline, I can able to manage it. I will take the extra classes also, but in online, it's not possible. And at the same time, it is not possible to you also. Sitting in the online class is more than 1.5 hours. Practically, offline classes okay, but online classes I know it's difficulty. But I will try to do my best, right, to teach you as much as possible. So I also from your part you have to learn, right, whatever we have seen so far. At the same time, I already shared some notes to you also, right? So whatever it is, all the things are basically using only basic differentiation and integration. So if you know some trigonometric identities, and if you know certain differential integration methods, you can easily able to understand the problems, right? So I will do my best, right, tomorrow class as well as probably if next week is not possible because Wednesday, Thursday, Friday are all holidays. So after Diwali, before the pre-Wednesday exam, right, I to do my best. So at the meantime, you also to be attentive, and you have to be doing problems, right? So at least if you study 3 units in a proper manner, out of 10 questions, you can easily rate all the 5 questions, and you can easily get 100 out of 100 itself, provided even if you study only 3 units, right? Anyway, we'll see, right? Because previously definitely we'll have minimum 1 month time between cat 2 examination and pre-university examination, but that time it is not possible. Or sometimes you have time at least after pre-university exam, before university exam you have some time, but that time also it is not possible because pre-university is 15th, then you have practicals, and then you have university exams from 29th onwards, right? And we also have to manage other things also, right? Apart from the teaching online classes, right? Preparing for examinations, all things also, right? So anyway, so with that I stop my lecture now, right? So I will take the attendance now. So all I expect from you is your cooperation in studies, because you are studying for yourself. Yeah, I'm not going to write the exam.